but I'm going to come from a very, very physical viewpoint of what you should be looking at when you do space-time diagrams. And remember, these things are super fluid. And these diagrams, they could be a real big pain in the ass. And what I mean by that, they could become overwhelming, like really, really quickly. My goal is only to use them to enhance the physics, nothing else. If it doesn't enhance the physics, I want to toss them out, right? Then it's total bullshit. We don't need that. So what we want to do here is that I'll draw them to the best of my ability that portrays the best physics. So when I think about problem-solving strategies here, what I'm really looking at here is that I'm going to be looking at things that are really quite basic. There's not a lot here, okay? There's not a lot here. And this is what we find here. There are two invariants that all observers agree on. Okay, one of them is the relative velocity. And actually, it's one of my most powerful ways of actually sort of like making calculations. You know what? I'm going to put on my headphones so that I don't hear anything else in case somebody asks a question. Then this way I'm muted from anything that goes on in my household. Okay. So then the next thing, so when I think about the relative velocity, this is an invariant. That means an observer from the S frame is going to see the exact same relative velocity with those two ratios. This seems like such a simple equation, but man, is it powerful. I mean, I kind of rely on that one quite a bit. And really, this is the more physics way to approach things. And of course, the other invariant is that this guy's always a constant. Those are the two things that we can rely on this thing here. And one of the things that we also have to worry about here is that we have the Lorentz boosts. And the way the Lorentz boosts work here is that the way I set it up here is that when I think about time dilation, I mean, I typically just kind of write this right here. And then once I have this, then I decide which frame am I talking about? Am I talking from the proper time of the S frame or the prime frame? So that prime is very fluid in this case. So of course, if I'm talking from the standpoint of, let's say, the rocket frame, then I put my prime right there. If I talk about it from the Earth frame, then I'm going to put my prime here. So it depends on the frame viewpoint that you're talking about. I mean, you got to admit that these equations are not that challenging. There's only one chance that I think of that you'll be challenged to use the full Lorentz equations, and you'll see why as soon as I write that down. And the other one, of course, is length contraction. So when I write this down, I almost always write it like this. And then I say the exact same thing as before. From what frame am I talking about? And I think this can get really slippery. So it's either going to be something like this, or it's, or it's going to be something like this. depending on how you look at it. And, and of course, gamma is 1 minus v squared c squared, which I typically write as 1 minus beta squared. And then the other thing here is that I always draw a picture of the situation. And what I mean by a picture, I really mean one of two things. I literally draw a sketch of what's going on, or I mean a space-time diagram. The job of the space-time diagram is to help you solve physics problems. That's it. It's not supposed to do anything else. It's only supposed to solve physics problems. And that's that. So what I want to do here is I want to just start jumping into the examples. Okay, let me get my example stuff. And the first one that I'm going to deal with, so I'm going to deal with example 1.1. So I'm going to bring this guy in here. And make this nice and big so that you can see it. Right, so this is a fairly straightforward problem. Okay, this is a fairly straightforward problem. And one of the things that I'm really...
Carlos, could you scroll up for a sec, please, just so I can get the part right above? Thank you.
Okay.
Starting at the second point, if that's okay.
Yeah, so the thing so let's read this together and let's see what this actually is telling me here. And then you'll see how I really change my space-time diagrams to help me more than anything else. So it says, when Spock returns his Hertz-Renner rocket from 1 week cruising in the galaxy, Spock is shocked to be billed for 3 weeks rental. Assuming that he traveled on a one-way trip at the same time, at the same speed, how fast was he traveling? And then plot a space-time diagram of Spock. So so there's a trip going to one place, and then there's a trip going back. And so what I want to do here is that I want to just focus on just one trip, that one leg of the trip, that is. Okay, and note, there's something special here, right? There's no space measurements here. Right? There's no space measurements. So the only thing we really care about is time. That's it. Okay, so then what I want to do here is that I want to start to move up here. And what I'm really seeing here is that I have 2 frames of reference that are perfectly legit, right? The principle of relativity implies that rest or constant velocity, that these 2 frames are good for doing physics. That means that both people are right regardless of which frame they're in. Furthermore, you can't even tell that you're at rest or moving at constant velocity. So when I think about this picture here, you could imagine Spock. Where's he? I don't know where he's renting his rocket from, but I know that Spock comes from where? Vulcan, we assume. And he's probably going out to what? Some vacation spot. Let's call this vacation spot. And what they really tell you when you think about this vacation spot and Earth and this Vulcan here is that they're actually in the same frame of reference. Okay? So if they're in the same frame of reference, then when I think about Spock and the rocket, what I'm really imagining here is that I have my rocket, right? And as it's moving, of course, the rocket is doing what? It's moving relative to the Earth. So Spock is in this guy here, and we typically call this the prime frame. So that's sort of like the customary view. But note, the principle of relativity says that that's a bunch of bullshit, what I just said. That's only one good frame. The other good frame is what? Is that when I look at Vulcan and this spot here, what I'm really seeing from these guys is that they're moving. Right? And you're probably just saying, well, you know, if you're anything like me, when I first started out, I'm going like, that's not true. The rocket's moving, and the Earth and the vacation spot are actually stationary. The principle of relativity says, no, you're wrong. They're both exactly the same and symmetric. So essentially, when we're looking at this trip here, what we're seeing here is that depending on your frame of reference, if you go and you look at this space-time diagram for these two situations, they should be identical. So let's pick one of the frames here. So if I look at this spot here, let's go look at this thing. So we agreed that Vulcan and this vacation spot are two different locations. So let's look at that. Since they're in the same location, excuse me, the same inertial frame, then that means when I look at these spots here, I'm seeing that the Earth and this vacation spot are actually doing what? They're not moving through space. They're moving only through time. So I gotta be really careful here with my notation because I don't want to mislead you here. So when I look at the Earth and the vacation spot, they're moving along this direction, but I'm gonna say that their speed through space-time or through space is zero, right? They're just moving through time. That's it. But in this frame of reference, what's actually happening? The rocket is moving. So when I look at the rocket frame, it's moving like this. And if I was to look at the rocket frame, let's call this the CT prime frame. In the rocket frame, what does this rocket frame do? Well, the person in the rocket frame, since we're only talking about time, according to our picture, these guys are actually moving in this frame of reference with a beta that's not equal to zero. So picture-wise, what I'm seeing here is that the space-time diagram is saying that as these guys move up the time axis, you could see that the time axis of the rocket is going to intersect with this vacation spot. Now, if suddenly the rocket only stays at the vacation spot, what's going to happen to the rocket? It's going to be in a frame of reference with the vacation spot. So then all of a sudden, it would move along this line now. And note how this green line is dashed. That's telling me that that's the path that the rocket would take along that time. But note, I haven't talked about distance at all. Why didn't I talk about distance? Because the problem doesn't talk about distance. It only talks about time. So I'm focusing only on the time axes. I hope that's clear. I'm only focusing on the time axis. So if I was to now read the question, note that there are two things here, right? So if I read the question here, it says that when Spock returns to his Hertz, when he returns his Hertz Renner rocket after a week of cruising, what do they mean by a week of cruising? Whose frame of reference is that?
Must have been his, because he was surprised by the 3-week spell.
Right. So it has to be that. So that means in his frame, now we got to be really, really careful here. In his frame, that dot right there equals 1 week. Now, if I was to compare with the Lorentz boost transformation from what does Earth say? Well, that means I have to do a boost from this frame into that frame. And as I do that, then that means, see, I'm getting into trouble here. See that beta? I got to erase it. That means beta going. Now note, if I wasn't here telling you, if somebody says like, what do you mean beta is going in that direction along that time axis? Remember, that's wrong. Technically, that's wrong what I'm drawing, but I'm drawing these to give you a sense that the rocket is moving through space, but the Earth and the vacation spot are not moving through space. They're only moving through time. That's what I mean by that beta. Because it's a bunch of bullshit for me to write betas on here and go like, oh yeah, this is what it means. It doesn't mean that. This is only to conceptualize what's actually happening in the picture.
Yeah, Carlos, real quick, why are we using the CT prime axis to basically show the trajectory of the rocket, not like the...
Okay, so let me ask you this. So do we agree that in the rocket frame, it doesn't move?
Sure, yeah.
And so if I'm only focused on time, the rocket doesn't move a distance x. It only moves through time. And up here, one of the things that I said here is I said there's no space measurements that they're talking about. So I'm really only doing a one-dimensional problem. I'm only focusing on time. Now, if I had space and time, then I would need to be drawing time and space simultaneously. I only did this thing here as a reference, so you knew what I was talking about. And the only reason why this is a reference is because there is a distance between the Earth or Vulcan. This is the Vulcan, vacation separation, right? Those two are completely separated. And that's why the time axes have to be separated, and that's why I drew that distance axis, so you understood that that's what I meant by that. So then, if I want to go measure this time relative to Earth, then essentially what I'm doing here is that I'm doing what? I'm essentially doing a transformation from here to there. And in that transformation, we know that relative to Earth, that's a 3-week period for Earth. So physically, when I look at a space-time diagram, if I'm only dealing with time measurements, I'm essentially talking about these two things right here. So if I then look at this thing here, you can clearly see that if I talk about time dilation, what that means here is that, look how I always start out. I look like this. And then I know that this has to be the larger value, and this guy has to be the smaller value. And remember what larger value means here, that it takes longer to make one full revolution, whereas the clock that has a smaller value makes that revolution faster. So then clearly Spock has to be in the shorter value. So then therefore in this rocket frame, this must be Spock. In this Earth frame, this must be Earth. So therefore I could then solve for gamma. And if I solve for gamma, you could see that gamma then is going to be the time measured relative to Earth over the time measured relative to Spock. And you get this factor of 3, which is 3 over 1. And then if I mathematically solve for this thing here, this is really what? 1 minus beta squared. If I do the algebra here, actually, I'm going to change what I just did here. I'm going to take this and I'm going to move it down. Oops, my bad. I want to take this whole thing and I want to move it down to here, because I want that space. And so if I solve for beta here, you'll get beta to be 0.94. And that's what you get right there. But I could draw the space-time diagram for the other scenario here, right? I could draw it for the other scenario. So if I look at this scenario here, note that this picture is quite different. So what I do here, and most textbooks don't do that, I actually switch my C, T, and CT prime. So now the only frame that I care about is the frame of the rocket. And what is the frame of the rocket doing in this scenario here? Well, according to this situation, which direction is the Earth moving relative to the rocket frame? Well, the Earth is going to be moving in which direction? Well, it's going to be moving away from the rocket, and the vacation spot is going to be moving towards in this direction right here. And so when I look at the rocket frame, I imagine that I have my rocket here. And in this scenario here, because I'm in this rocket frame, I'm going to lie and just say, hey, that really what I mean by that is that it's not moving through space, it's only moving through time. And so when I look at the other locations, right, what I'm seeing is that these guys are moving. And as they're moving, I could see here that they're moving not only through space, but they're also moving through time. And this picture's totally legit. So all I do is that if I'm really in an inertial frame of reference, I cannot tell that I'm moving. Remember what I said about that Home Depot experience that I had? I pull up to the ramp, it's early in the morning, and I think that, I'm good, and then I don't even realize that the truck is moving, and I slam on the brakes, going like, oh shit, I fell asleep. My car's rolling back. The rocket frame cannot tell that they're moving. Right? In this frame, the net force is 0, so you feel nothing. So I can't tell the difference between this picture here and this picture over here. But that means if I was to look at how long does it take for the vacation spot to reach the rocket, well, we just solved that problem. It's going to take what? It's going to take 3 weeks. And it's only when we start to compare clocks, then we start to go like, oh, there's a problem. The rocket had to have accelerated. The rocket had to have decelerated. Now I know which clock is moving. So according to the rocket, so the rocket frame, it then says that it took what? That it takes these guys 3 weeks to come. So this means that the time of the, no, I don't want to write that because I think I'm going to start confusing the issue. But all I'm saying here is that these two are symmetric, right? These two situations, they're symmetric in special relativity. That means zero acceleration. Each of them can say that they are right and the other's clock is time dilated. So I just wanted to keep drawing those pictures so that I could show you what I mean by these pictures here. So then that's part one here. So what I want to do here is that I want to come in and I want to look at a second one.
Wait. When you plug in 3 times 1 divided by 1 minus beta squared, and you solve for that, do you get like 2 and then square root 2 and then over 2 and then you try to simplify that?
Right, so yeah, I mean, if you just simplify it, right, if I square each side, this is going to be 9.
Okay.
1 minus beta squared. Right, and then if I reverse this,
Yeah, that's right.
I'm going to get beta squared is equal to 1 over 9.
Yeah.
And then once you do that, then you get that value.
Okay.
Okay. So what I want to do next here is that I want to go to this next one. So if I continue to move in this direction, what I want to do this time is that, as always, I'm going to ask the question, draw a picture, and then let's draw a space-time diagram. And remember, the space-time diagram and your sketch of the situation is to increase your ability to see the physics, nothing else. So it says here, Antonio sets off at a speed of 0.95 c to a distant star. After exploring the star for a short period of time, he returns at the same speed and gets home after a total absence of 80 years, as measured by an earthbound observer. How long do his clocks say that he was gone, and how much has he aged? Okay, so what I'm thinking here is that I can come here and I could immediately say that the sketch of the situation is identical from the previous one. Okay? It's identical. And so what I mean by that, if I scroll up a little bit, you could imagine that I can't tell the difference between this image or that image. They're both symmetric for each observer. But this time I only looked at a one-way trip. Now I'm going to look at a two-way trip and what actually happens here. Well, for starters here, if you're going to return here, the image that I actually see in my head here is that I'm seeing what? So once again, when I look at the scenario, note that there is no spatial reference here. So believe it or not, this is a one-dimensional problem. It's really about two different times. So I know it's, I think I said that a little bit too fast. It's not a one-dimensional problem. It's a two-dimensional problem where I'm dealing with two time axes. But I'm still talking about time. And I mean that there's no space, only time. So I am dealing with the two-dimensional problem, two different time references here. And so what you're really seeing here is that it tells you that there are three frames. And what do I mean by three inertial frames? I think that the three frames that I'm talking about here is I got to be talking about the Earth frame, I got to be talking about the star frame, and I got to be talking about the rocket frame. So, but there's going to be a problem here. And the problem is that if I'm looking at the return situation, then I imagine that I have my star here, and then of course I have my rocket. So then if I start to look at the scenario here, what I'm really seeing here is that there's this star out here, and I know that these two guys are in the exact same inertial frame of references. So the only thing that's really happening is that I know that this guy's moving at 0.95 C relative to what? The Earth star system. So now I know that my prime frame is going. So what I'm seeing here is that I'm seeing two pieces here. Well, technically, what has to happen here is that there has to be a what? There has to be an outward trip where I go from Earth to the star. There's got to be an outward trip. So that means when I look at my time, I'm going to call that T1. And then what happens here is that if you really want to be technical, this guy actually has to move around the star and then make a return. So there's a point here that when we look at this thing, there has to be a turnaround. And when I look at the turnaround, I'm going to call that T2. And then it has to come back from the star to that. So then there has to be the return trip. And I'll call that T3 here.
Carlos, for your notes, the S prime frame in the middle is missing a prime.
Thank you. So when I look at this thing here, if I'm really being technically correct, there is a total time for the trip, and it must be these guys right here. The one issue here is that we can't answer this one. Why? Because there's acceleration. And to deal with acceleration, we need the general theory of relativity. So what we're really saying here is that we're just going to ignore that piece. But there's a reason why I want to bring this up, and it's because of the space-time diagram. And I'll be very clear on the space-time diagram. So now what I want to do here is that I know that that time and this time, they have the same speeds, but they have different velocities. So that means I have to have a change in slope in the velocity or the whirl line of the rocket. So what I want to do here is that I want to think about what does the space-time diagram look like now? Okay, so let's draw the space-time diagram. So when I look at the space-time diagram, it says that it took 80 years relative to the Earth. Okay, so this is telling me that the total time relative to Earth, it took 80 years. And there's an assumption here, and the assumption is that that means that half of this outwards and half return. Right? That's what we really mean. And so what I want to do here is that I want to draw this picture to see what actually makes sense here. So here I go. I have two frames of references that I have to consider, the Earth and the star. I agree that they're in the same inertial frame of reference, but they are spatially separated. So when I come in and I draw them, I think about something like this. And these are both CT here. And because these guys are separated spatially, this guy here represents the Earth, and this guy represents the star. And they're moving through time in this inertial frame of reference here. So now, what I got to do here is that I'm going to draw a line. Now, I got to be careful with my lines here, but I'm going to tell you that I'm going to cheat here. And the way I'm going to cheat here, I'm missing something. Hold on a second. What are my tools of the trade? Damn it. Well, you know what, I need my, okay. Look at this. This is my UC Santa Cruz ID when I was a graduate student. That was over 30 years old. This is my straight edge now. So check it out. So what you want to do here is that I got to think about the rocket frame. So when I think about the rocket frame, what's actually happening here? Well, I know that the rocket is moving relative to this frame. So what I'm going to do here is that if this is truly a 45-degree angle, squint so that it's not 45 degrees, because remember, 45 degrees means you're moving at the speed of light. So what I'm seeing here is that I'm seeing my rocket frame now. So my rocket is moving along here, and it's moving at some beta along this frame of reference. And what we know here is that there's a certain time. It takes 40 years to go outwards. So that means here, so when I look at the Earth's frame, then that means at this time right here, this must be 40 years in the Earth's frame right there. So again, what do I know? In this frame here, I have what? I have the star frame. In this frame, I have the Earth frame. So when I'm looking at these guys, what you're actually seeing here, you know, note that this guy's still moving up the time axis, but, you know, this star is also right here, right? That is the star when it reads, but then it continues to move along the time axis as it does this. So then what happens next here? You could see here is that as I go along right here, this is the outward trip, and then there's the return trip. Now, the thing about this thing here is that this guy is really CT prime. When the rocket turns around and then heads back, note that the slope of that line has to change. So how am I changing this? Well, what I'm going to do here is that I'm going to draw a line that's supposed to be symmetric between these two. I'm sure it's not going to be, but then the rocket now moves in this direction. So if I'm looking at my little rocket is moving in this direction as it goes that way. And again, my beta is the exact same value as before. It's just that the velocity has changed. So if I was to follow this line right here, right, it would have this dashed line that I'm going through the Earth, but I'm not. So what I want to do here is that I want to draw a parallel axis. And this is a different inertial frame. So I'm going to call this C double prime, CT double prime. And so what you're seeing here is that the outward is what I defined as prime. And then the return, I'm calling double prime. And note that these two lines here are parallel. So you could see that there are two time intervals. There's this time t3, and then there's this time t1. And these are the times that I'm talking about here. But picture-wise, they really allow you to sort of like physically see what's going on here. So the question is, what is this time coordinate? Okay, what is that time coordinate? In other words, what time does the spaceship, captain read? Right? So if I keep going along this thing here, one of the things that we find here is that from that frame of reference, I do know that I come in like this, and I'm asking, typically, I just say, so what frame am I going to look at? Well, what do I do know here is that in the Earth's frame, by the way, I missed something up here. This is 80 years up here, because that's what the question tells me. So, but in the Earth's frame, we know it's 80 years. In the rocket frame, we know that that has to be the proper time. It has to be the shorter time. So that means that in this spaceship frame, which I'm calling prime, then I'm going to come in here and I'm going to put my gamma where it's appropriate. It's got to be right here. I could have put it on the other side, depending on which frame that I'm talking about, but from the frame of the Earth, it's the rocket that is moving, and it is the rocket that has the time dilated time. So then what this is telling me here is that this allows me now to do what? Calculate the proper time of the spaceship. So if I do that, then that tells me that I could then say that the time in the spaceship right? Because look, I'm on that CT prime. I need that coordinate right there. That then has to be that of Earth divided by gamma. And in this case here, I'm going to get that this should be 1 minus 0.95 squared, square root. Ooh, I made a mistake here. I'm writing that wrong. It should be 1 divided by the square root of 1 minus 0.95 squared, divided into the time of the Earth, which in this case here should be 40 years. And that's going to give me that one coordinate system. So if I look at that one value here, then I'm going to get 12.5 years. And this is what the spaceship reads when it gets to that star, which is the prime. So that means then I now know what that coordinate system is. That coordinate system at this point here should read 12.5 years. So according to the spaceship, assuming that they're truly symmetric, so a symmetric time path for the spaceship should then be that the total time should be twice that of the spaceship just going one leg of the trip, which would then be 2 times 12.5, which should be 25 years. And this is the total time to go back and forth relative to the prime frame. So one of the things that I wanted to address here is that I wanted to look at the times here. So initially, I want to address.
Carlos,
Yes.
you're going really fast, and I kind of got lost. How did you get the 0.95?
Oh, because it's part of the problem.
Oh, it's part of the problem. Okay, okay,
So when you look here, look at that. You're traveling at 0.95.
okay.
Okay. So one of the things that I want to address here is I want to address the turnaround time. And what we said here is that when I look at the total time of the spaceship, it's going to be what? It's going to be T1. Let me take the prime off here. T2, T3. We just did this guy right here, and we just did this guy. So the question is, what does this mean physically? And what I really want to do here is that, I know, Michael, this is going to piss you off, but it's okay. I'm going to copy and paste right here.
It's fine. I'll have the diagrams in your notes. So
Yeah, it's just because I want to take a lot of the crap that's there off. So I'm going to paste this thing here. And what I really want to do is that I want to come in and I want to erase all of this. Okay, I want to erase all of this stuff here. And I really want to focus just on this piece right here. Okay. So the question is, we've said already that what this really means right here is that this is T1. Up here, if I take this piece off here, right, this is T3. So the question is, where is this time T2 at? And this time T2, what it refers here is that what you're doing here is that you are changing inertial frames from S prime to S double prime. Now, when I say inertial, that means that this is moving at what? Constant velocity. This guy is at constant velocity. So if I was to sort of like, write this out, I would call this V prime, and I would call this V double prime. And what you're seeing in this scenario here is that V prime is not the same as V double prime. And the reason why that is that even though they have the same speed, they have opposite directions. So that means, look at the prime frame right here, right? So if I look at this prime, this is C double prime, CT double prime. What I'm doing here is that I'm accelerating from this frame of reference, okay? I'm accelerating from this frame to that frame right there. So if you were to use the general theory of relativity, you would then get this time t2, the time it takes to go from the prime frame to the double prime frame. And that's where that delta t2 time comes from. It's the changing of the inertial frames that causes you to do that. Because nature does not have any sharp discontinuities. Okay? There's no sharp discontinuities. Okay, that's what I wanted to address here. Okay, so let's move on. Okay, so what I want to do here is that I want to come back and I want to get the next question. And in this scenario, what you're going to see here is that this may look like a very similar problem to what we've been doing, but believe it or not, I'm going to look at it differently. So the other techniques that I've been showing you are very similar in process, but here, what we want to do is that we want to look at, there's a different way of looking at this thing. So what you have here is that you have a spaceship that departs from Earth for the star Alpha Centauri, which are 4 light years away, Actually, it's a series of stars, right? It's not just one. And then the spaceship travels at 0.75 C. How long does it take to get there as measured from Earth and as measured by a passenger in the spaceship? Then it says draw a space-time diagram. Okay, so again, this picture is very similar to what we've been drawing, but I want to take a slightly different viewpoint on how we actually look at this thing here. So if we look at this thing here, there's a couple of pieces of information that are important. When they say 4 light years away, what do they mean? In what frame of reference are they talking about when they say 4 light years away?
Earth's
Frame?
Well, yeah, it has to be relative to the Earth and the Alpha Centauri star, right? So I have these guys here that are telling me that they are in the same frame of reference, and that means an observer in both of these forms and both of these observers would always say that this guy is 4 light years away. And just to make sure that our language is correct, 1 light year, which is written CY, that's just the distance that light travels in 1 year, and this is roughly about 10 to the 16 meters. Okay, so that is a long, that's pretty far, of course it is. So the thing that's special about this time, so I'm going to call this AC for Alpha Centauri, and I'm going to call this guy Earth, of course. And we know that the spaceship is traveling just because it's telling us that the spaceship is traveling. So typically, me writing this expression right here is what? Not very RC. Technically, I can't say that. I can't tell you that the rocket is moving. So, but when I make that statement, I know that I have this little dude here, and he's telling me that the rocket is moving relative to him. Okay, but the problem, just me saying the spaceship travels at 0.75 C, I'm already relativistically incorrect. It's wrong. Why? The principle of relativity says you cannot tell the difference between being at rest or moving at constant velocity. Only when you accelerate can you make that statement, I am moving. But if they're in an inertial frame of reference, you cannot make that statement. So because this dude on Earth tells me that I'm moving relative to him, then I'm going to say, okay, yes, this guy's moving at 75% the speed of light. And so now we know that this observer is measured from the Earth Alpha Centauri. By the way, if you had this indestructible suit and you were standing on Alpha Centauri, he would also say that the distance between him and the Earth is 4 light years away. So both observers agree on that. So the question is that now we have a distance here. So when I look at my space-time diagrams, moving a little bit faster here, I have two inertial frames that look like this. And we already said that the distance between these guys right here is 4 light years, right? If they're 4 light years, and of course, I mean, obviously the Earth and this guy are all moving relative to time, but not space, right? They're moving with beta equal to 0 as they go up. It is the rocket that is moving. So it is the rocket that moves. So as the rocket moves, what we're seeing here is that it catches up to, right? The rocket is moving in this frame right here. And as it moves along this frame, it's essentially going to coincide with this guy as it moves in this direction right there. So this is the destination that it gets right there. And so I can say that as soon as it goes into here, right, this is what that line would be, it now moves simultaneously with the Alpha Centauri because they're now in the same location, and then they just move forever in that space here. So the question is, if I ask the question, how long does it take to get there as measured from Earth? So here's the question. From Earth's viewpoint, how long does it take? Right? How long does it get there? Well, here's what's really nice about this thing is that we know that the relative velocity is a constant. And this guy is 7.75 C here. But all observers measure this speed. So that means here, I could then look from the Earth frame, I could make this statement right here. And the beauty of this problem here is that, look, we know that distance right there. This is known. And because this is known and I know what the relative velocity is, I can instantly calculate what the time is relative to Earth. So what this allows me to do then, I can immediately determine the time measured by delta t Earth. So how long does it take the rocket to get there relative to Earth? Well, if I know delta x and I know delta t, if I know delta x and v, then clearly I can get delta t of Earth as being delta x of Earth. Maybe I should be saying AC here. And then this is going to be the relative velocity. And then if I look at this mathematically, then clearly this guy is 4 light years. This guy is 0.75 c. You could see here that the c's cancel out. And so when I compute this value, I end up getting a distance of 5.33 years for the time measured on Earth. Right? That is the time measured on Earth. So what does this time of 5.33? Well, that means that when I look at this time right here, if I do some transformation, this time in the Earth frame is then going to be 5.33 years. That's what I just calculated. And the thing about it, note that I didn't have to spend any thinking like, oh, is it the Earth that's moving? Or is it the rocket that's moving relative to me? It's because of the relative velocity. It's got to be invariant for all observers. So that being the case here, then what I can do then is that I could come in and then I could, say the exact same thing. If I look at this from the frame of reference of the rocket, right? So from the frame of reference of the rocket, I'll draw this faster now because we've done this a couple of times. What do we know about the rocket? What we know here is that this guy in this frame, it's stationary. The rocket's not moving. It's stationary in his frame. So when I look at the space-time diagram, I draw the exact same thing that I've drawn in the past. See how conveniently I keep redrawing these guys? So when I look at these other things here, what am I looking at? Well, I'm looking at this guy, looking something like this, right? And this frame right there, this is my, this is my T prime. And then if I look at this exactly the same way, I could imagine that this guy's also here. And again, this is actually moving what? It's moving in this direction as well. And so here's my Alpha Centauri, here's the Earth. And when I look at my rocket frame, I'm really thinking about what? That there's my frame right there for the rocket. And when Alpha Centauri gets to the rocket, right? That's the crazy thing. It's not the rocket getting to Alpha Centauri. It's Alpha Centauri coming to the rocket. It takes how long? 5.33 years. It is truly symmetric. So I have a stationary rocket with Alpha Centauri coming at me at beta equal to 0.75, right? So picture-wise, it's coming at me at beta. And how long does it take? Well, it takes 5.33 years to get there, right? That's what I mean by this thing here, right? That's what I mean. So,
Hey, Carlos.
yes,
And when you're saying it still takes 5.33 years, you're not talking about in the frame of the spaceship, right? You're saying like
no, it is in the frame of the spaceship.
still takes 5.3 years. I thought the 5.3 years was from the frame of reference of Earth.
But then when you make that statement, then you're saying that the Earth's frame is the preferred frame,
Ah, okay. Thank you.
right? But there is no preferred frame, right? This shit is crazy, right? I mean, you look at the mass of the star and you look at the mass of the rocket and you're going like, damn it, there's no way that star is moving. But special relativity says bullshit. It is moving relative to the rocket. How do you know that you're driving down the highway, right? If you're thinking about the highway, right? If you're thinking about the highway, you could imagine that you're driving down Highway 1, and we all hope and agree that the Earth is sort of like spinning, right? How do you know that I don't get in my car and I sit there and I wait till the Earth rotates Cabrillo College to me? And then when I want to go home, I just sit in my car and then the Earth rotates away. All you got to do is, you know what the great thing about it is that you could save a lot of gas that way, right? But you know there's a problem because you're putting gas in your car. Or in my case, I'm charging my car, right? That's a very skewed reality. And this is where I keep going like, dude, I don't like this reality sometimes. I go like, that's bullshit. But when you do measurements, and remember what I said about these measurements, there's trillions upon trillions over decades and decades and decades. This thing is never violated. Never. And that is crazy, right? That really worries me when people say that. But
Carlos,
yes,
since I know this is not relativistically correct, but since the ship is moving
relative to Earth, right?
relative to Earth,
Yes, I agree.
doesn't the space contract, and so it doesn't actually travel 4 light years, it travels less, so shouldn't it do it quicker? Or we're just not allowed to say that because the ship would say Earth is moving.
Yes.
And so Earth's space contracts.
That's right. You are not, like you said it already, you are relativistically incorrect. You're not RC. Frustrating, isn't it?
Yeah, I'll just stew on that for the rest of my life.
But now you're right. So if I start to look at that, you did say that there is contraction. So if I start to look at this thing, we know that relative, but now we're going to take from relative to the Earth observer, we know that there is time dilation, and the rocket passenger or the rocket captain feels the acceleration. And as he feels the acceleration, he then says, I am the one moving. Right? Without that, you could not make that statement. So then, what do I know? Well, we know that from the rocket frame, there has to be a time dilation. And the way that time dilation has to be here is that we know that when I draw this out, right, I'm talking about Earth and I'm talking about the rocket. And the question is, where do I put my gamma? If I'm in the rocket, then I have my own proper time. So therefore, that has to be the dilated time. And if that's the case here, then I come in and then I put my gamma in the right spot. So then I could then solve for delta t prime of the rocket. And you could see that algebraically, I mean, it's fairly straightforward. Over this gamma factor. And so then I continue to write this out. So I know that the Earth measures 5.3 years in its frame. And then I have my gamma factor. And that's going to give me a shorter time. And the time that I read then is 3.53 years. And this is the time of the rocket.
That's the time of the rocket relative to Earth?
Well, remember, relative to Earth, we already said that was what? 5.33 years. So this is relative to what the rocket is measuring. This is the proper time of the rocket. Okay? Remember, own proper time. And so that means if I now go back to my diagram, right, if I kind of scroll back up here, then I know what that time is right here. Right? My diagram then says that what is this time that the rocket measures? It's going to measure 3.53 years in my space-time diagram. Okay, so that completes that space-time diagram. Now, what I want to do here is that I want to keep moving along the same directions as this problem so that you see problem solving slightly different. And what you want to think about here is that one can compute the contracted time or contracted length, you know. And the way you can calculate the contracted length, if you think about this, we know everything about this Earth AC system. We know the time, we know the distance, but this is exactly as what? The observer on the rocket says that I also see that relative velocity to be the same. And what we just calculated right here is that I calculated what? This guy right there. But we know what this velocity is. So you could see here that the contracted length as measured relative to the rocket then here has to then be v times the time of the rocket. And note that I don't have to say, which frame am I talking about? Am I talking about this frame or am I talking about that frame? It's just the relative velocity equation says, no, That's an invariant for all observers. So if that's the case, then I know that the speed is 0.75 c. My time at the rocket we saw is 3.53 years. So therefore this distance here is then 2.65 light years. And this is the distance that the rocket measures. I could have brought in the gamma values and put everything in. I find this to be more intuitive, to be honest here. So the statement is, if I really come back to the picture that I was talking about earlier, right? So the picture that I had is this. I have the Earth, I have the star. And the rocket is essentially taking off from this spot right there, right? So I got my rocket, I got my Earth, and I got my star right here. So when I'm looking at this guy, we're saying that when the rocket is leaving, what does it actually see here? It doesn't see Alpha Centauri in this frame. What it sees here is that it sees this guy right here. It sees a different distance of 2.65 light years. And you may ask the question, but isn't it really 4 light years away? And the answer is no. No frame is preferred. Different measurements, right? The rocket measurement is not the same as the Earth measurement. These are not the same. Both are correct, right? Both are correct, not one. Both. There's no preferred frame from the special theory of relativity.